Hey, my name is Patrick Lambix, and I work at Linköping University and part-time at the University of Gävle, both in Sweden. In this talk, I will introduce a method for extending ontologies. First, I will give a short motivation, including a reminder about what ontologies are. Then I will introduce the method, as well as some ongoing work on a tool that can be used in the workflow of the method. And I will end with a brief conclusion. So ontologies have been suggested as a technology to make data fair. For this audience, and considering the previous talks in this workshop, I do not need to explain further anymore. So what were ontologies? Well, ontologies can be seen as a way to define the terminology in a domain by defining concepts, relations, and axioms. And here is an example of an ontology that we developed and that aims to represent essential terminology regarding materials design. There are some core concepts in red, such as calculation, property, structure. There are some concepts related to computation, such as different computational methods, some concepts related to structure, and then some related to provenance. Further, there can be relationships between concepts. So for instance, there is a relation has output structure between a calculation and a structure. There are also axioms, in this case to represent is a relation, where we have a hierarchy of different computational methods. So the way that we use this ontology is in an ongoing project where we aim to provide semantic and integrated access to materials databases. We currently work on the databases in the Optimate consortium, where the idea is that by using the ontology and by creating mappings between the schemata of the databases and the ontology, we will allow querying over multiple databases and will allow queries to take into account relations in the ontologies. In the paper mentioned at the bottom, there are some examples of queries that could not be asked using the current interfaces of the databases, but which you can ask and you would get results using the ontology because the information is actually in these databases. So to be able to provide good services, it's needed that these ontologies are of good quality. And I will focus on one particular quality aspect, namely completeness. So the idea of completeness is that we want an as high coverage as possible of the necessary concepts, relations, and axioms. In general, it's not very easy to say when an ontology is complete, but it is actually possible to define when a version of ontology is more complete than another version. And incompleteness can be missing concepts, missing relations, and missing axioms. Now, these missing concepts, relations, and axioms are problematic in semantically enabled applications, such as ontology-based querying. And here is an example for the influence of missing axiom. So we're querying PubMed here. PubMed is a database with over 30 million abstracts of research articles in the biomedical field. And we're going to query using scleral diseases. So we want the documents that are about scleral diseases. And in this case, PubMed will use MESH, which is a vocabulary, and it will take into account that scleritis is a scleral disease. So in that case, the system returns us 1,663 articles according to a query that I did some time ago. Now, what happens if this relation between scleritis and scleral diseases would be missing? Well, then the result would only be 948 articles, which means that a large part of the articles that are interesting for us are actually missed. So in the remainder of this talk, I will introduce a method to find new concepts and axioms to be able to make an ontology more complete. Our proposed method has two parts. In the first part, we use unstructured text, for instance, research articles, as an input. And as an output, we receive a list of frequent phrases, as well as topics which a domain expert then needs to validate. In the second part, we try to find additional axioms using formal concept analysis. So let's look a bit closer at these two parts. So for the first part, we use an existing system called the TopMine system. It's a data-driven system. It does not need any background knowledge nor linguistic rules. It works on phrases rather than on words, and it has two steps. In the first step, contiguous phrases are collected and counted, and phrases that occur at least as often as a given threshold are considered frequent phrases. In the second step, topics are generated. And essentially, topics can be seen as a probability distribution over words or phrases. So let's look at an example. This is an example from a biomedical text. Given a collection of documents, the topic model approach assumes that each document has a distribution of several topics, and each topic has a distribution of a number of words or phrases. For example, in this document where we look at topics based on words, the approach returns 4 topics. Each topic has several representative words with a confidence value to state how likely this word can represent this topic. So in the first topic, we have, for instance, gene, DNA, and genetic. TopMine will then represent the topic as a collection of phrases rather than words, as in this example. In our second step, the formal concept analysis phase, we use a topic phrase table. For instance, in this table, we can see that topic 2 is represented by phrases 2 and 3, and topic 3 is represented by phrases 1, 2, and 3. And comparing these sets of phrases allows us to conclude that topic 3 is actually more specific than topic 2. And thus, we could suggest a hierarchical relation between these two topics. Domain expert will then need to validate this. In the remainder of the talk, I will not get back to this stage because in the 2 experiments that we did, in the first experiment, we didn't find new knowledge that was not found in the first step. And for the second experiment, we actually didn't reach this phase yet. So in general, the domain expert is involved in validating phrases, topics, and axioms, and needs to decide whether concepts or axioms should be added to the ontology. Now, for our own research purposes, we introduced different validation categories, representing whether knowledge should be added to the ontology, this is the add label, or we should add this knowledge with a small modification, that is this -m, or whether the knowledge already existed in the ontology, the exist labels, or whether it is not relevant at all, there's a no label, or it would be a concept which is too general for this ontology, there's a no G label, or if it's too specific, and then we have labeled it with a Q. So let's look at 2 experiments. In the first experiment, we try to extend 2 ontologies in the NanoParticle domain. These are NanoParticle ontology with 1904 concepts and 81 relations, and eNanoMapper ontology with over 12,000 concepts and 4 relations. So we collected 627 abstracts from the nanoparticle information library. We experiment with different settings for top mine. The first number in the table tells us how many topics we want. This is a setting you have to provide beforehand, and we experimented with 20, 30, and 40. The low and high refers to how easy or difficult it is for words and phrases to be merged in longer phrases. So for the phrases generation step, we found, for instance, that amorphous silicon should be added to the ontology, and gold nanoparticle already existed in the ontology. The best result for the nanoparticle ontology suggests that there should be 32 concepts added with the same name and 4 additional ones with a slight modification of the phrase name. So 36 in total. It also found over 40 concepts that were already in the ontology. And existing concepts give us some kind of a sanity check that this method actually does find relevant stuff. For eNanoMapper, we found 32 new concepts. Similarly, in the topics validation step, it was suggested that mesoporous silica nanosphere should be added, and we already had chemical vapor deposition in the ontology. So for both the nanoparticle ontology and for eNanoMapper, we found 10 concepts that could be added, but actually only 2 of those were not found in the previous step. So there are actually ontology learning methods and systems, and these could be used for extending ontologies. And because if you can learn the ontology from scratch, you could also, in principle, use it for the extending the ontologies. So we wanted to compare our result with some ontology learning systems. We compared it to text-to-onto. It was actually the only system that we could download, but it is actually a well-known and very popular system. For extracting concepts from textual resources, it uses 4 algorithms. And as it returns lots of validation candidates, it's also word-based, we check the first 100, 200, 300, and 400 suggestions. And in this table, we show some results when we use all 4 algorithms. So in the precision part, we see that our system has a higher precision, which means that the percentage of the suggestions that are relevant is higher than for text-to-onto with up to 400 suggestions. But we also see that we have maybe similar amounts of new concepts that can be added. So what is the relationship between these sets of concepts? Well, here are just a few examples. And we know that some concepts, marked in blue here, are found by both methods. The blue ones, the green ones are only found by our method, and red ones are only found by text-to-onto. So it actually seemed that these approaches are complementary to each other. So now the question is this extending ontology actually worth the effort? Well, we spent about 10 hours per person for 3 experts. 2 of them were ontology engineering expert, and 1 was a materials science expert. For the nanoparticle ontology, we found 35 new concepts. We added 42 new axioms representing isorelations between sub and super concepts. And these new axioms actually led to changes in the sub and super concept sets of 72 already existing concepts in ontology. So that means that for 107 concepts, the results for queries using those concepts will become better. For eNanoMapper ontology, we introduced 32 new concepts, 37 new axioms representing isorelations between sub and super concepts. And this led to changes for 32 already existing concepts. And thus, for 69 concepts, the results for the queries will be better. We also note that if the concepts are used as domain and range restrictions for relations, there will be even more influence. So in the second experiment, we want to extend MBDO. It is still ongoing work, but the idea here was, can we actually use the ontology as a seed? So MDO is the ontology that I described earlier. And the idea now is to use the 32 concepts from MDO as a seed for our system. So we use these 37 concepts as search phrases to 2 databases connected to journals. And when we did that, we received over 8,000 different documents, where we only collected the title and the abstract. The reason for this is that we think that the main phrases and the main concepts in the field will appear in this part of the text. We did some pre-processing, such as only using lowercase, removing punctuations, removing words of length 1 or 2. And after this pre-processing, we had over 21,000 distinct words occurring together over 800,000 times. Many of these words appeared only less than 10 times, 72%, while these 17 words, which are very general, they occurred more than 3,000 times. Then we also used some stemming to remove redundant phrases and also to reduce the work of the domain expert. So all these phrases would be represented by one phrase, which is this one. And in addition to a minimal threshold for deciding whether a phrase is frequent, in this experiment, we also added a maximal threshold to remove phrases that may be too general. So for instance, it would allow us to remove these very general words by setting a maximum threshold of less than 3,000. So in this figure, we use as the base case a minimal threshold of 10. So phrases need to appear at least 10 times to be a frequent phrase. And the maximum threshold of 8,000, which actually no phrase reached. So essentially it means there is no maximum threshold. When we compare to other settings, we can, for instance, change the minimum threshold to 15, 20, 25, and 30. And when we do this, it becomes more and more difficult for a phrase to be called a frequent phrase. And thus, more and more phrases will actually be removed from the suggestions. Similarly, when we reduce the maximum threshold, more and more of these general phrases will be removed from the suggestions. Some phrases are also added, and this has to do with the feature in TopMine, which uses a quality threshold, and sometimes subphrases will attain this quality threshold when their super phrases are removed. We are still working on the evaluation phase, but here's an example of the results. For a minimal threshold equal to 30 and the maximum threshold equal to 500, the system suggests 131 frequent phrases, of which we may get 88 candidate concepts. So some phrases may lead to multiple concepts. Whether all of these 88 concepts will make it into MDO, this still remains to be seen. Now, it is of course possible that topics overlap with their phrases. And here are some results from 2 different settings. We see that the more topics there are, the lower the overlap will become. And the more overlap you have between topics may actually indicate that maybe there's a relationship between the different topics. And this may lead to new relations or axioms in the ontology. So in the first example, it's very likely that there is a relationship between topic 1 and topic 6. So based on the 2 experiments, we can make some general remarks. Our method is based on phrases rather than words, as we assume that other methods can easily find words that could lead to concepts in ontologies. So our method could be seen as complementary to those approaches. We also noted that a higher mining threshold for topics gives fewer phrases in a topic, and usually fewer phrases in a topic makes it that the results are easier to interpret for the domain expert. Now, something that is quite difficult is to decide on what should be included in the ontology. We need some more information, or we need to decide on the scope of the ontology beforehand. And this may be influenced on the application that we still have in mind. So for MDO, this is exactly the stage where we are now. The application that we envisioned is mainly, or at the moment, is semantic and integrated access to optimate. So this will influence what kind of concepts will make it into the ontology and which not. And further, it was clear that tool support is needed for the validation phase. In the first experiment, the domain expert validated the information in Excel files and also noted down which concepts and axioms should be included in ontology in these Excel files. And this is, of course, not the ideal way to do it. So in the remainder of the talk, I will show some slides regarding a tool for validation of phrases, which we're currently developing. At the moment, we've only looked at the phrases step. The topics step is future work. So the tool follows the workflow of the validation. First, it deals with the phrases. And then there's a step for going from phrases to concepts. Then you can add some concepts which are actually not related to phrases. And then finally, there is support for adding axioms as well. So for instance, in the phrases step, you can upload the ontology that you want to extend, as well as lists of frequent phrases. And these lists of frequent phrases can be generated by TopMine, as in our approach, or it could be generated by any other system. One of the things that you can do in this phase is, for instance, checking whether there are already concepts related to this phrase in the ontology that you want to extend. So here we have the list of phrases. And we're working on the phrase Hartree-Fock. And we see Hartree-Fock method is already in our ontology. In the next step, you can define new concepts based on the phrases, or by using the phrase as is, or by making some small changes. So for instance, here we have for using the phrase as it is, and here we have for defining a new form of the phrase. And here it shows which phrase we're dealing with. Then there is also a step that allows you to add new concepts which are not related to phrases. And this was a request by the domain expert where he found that he needed to add additional concepts inspired by what he was validating at that time. And the last step, we add axioms. So in this example, we are working with the concept electronic band structure type. It will appear in these in the pane. You can then select concepts from the ontology that you are extended, and you can then say, for instance, that an electronic band structure type is a property. And then it will appear in the system. The system will also tell you about some consequences of the decisions you make, for instance, cycles. So in this example, there is already information ontology that crystal lattice type is a Bravais lattice type. And now the domain expert wants to add that Bravais lattice type is a crystal lattice type. The system will then note that this would lead to the fact that these concepts are actually equivalent. And then let the domain expert decide whether to proceed or not. The system also has some other functionality. It is possible to search in phrases, concepts, and axioms. During the whole process, it's possible to take notes in the system. You can also mark phrases as finished processing so that you don't have to remember what you've finished. There is also some simple ontology visualization that shows both the original ontology as well as the added new concepts and axioms. And you can save your results in OWL and Excel. So as a conclusion, we proposed a method for extending ontologies with new concepts and axioms. The method is phrase-based and it's complementary to the word-based approaches. And I do think that extending ontologies to make them more complete is worth the effort, as it raises the quality of the ontologies and therefore the quality of the services that use these ontologies in semantically enabled applications. So let me finish by thanking some of my colleagues. Rika Tamiento is our domain expert, my colleague, and Guan Yu Li, Mina Apnikuripur, and Ying Li are our students. And we also thank the Swedish Research Council, the Swedish eScience Research Center, Swedish Agency for Economic and Regional Growth, and the National Graduate School in Computer Science for their financial support. Thank you for listening, and if there are any questions, I'm happy to take them.